Hey guys, welcome to our new lecture. In today's lecture, we are talking about Eulerian and Hamiltonian cycles. When we talk about Eulerian, we mean there is a walk that passes through every edge exactly once. When we talk about Hamiltonian, we mean there is a cycle that passes through every vertex exactly once. This is the difference between them. Eulerian means visiting every edge exactly once, and Hamiltonian means visiting every vertex exactly once. There are 3 sections in this lecture. First, we will learn Eulerian trios and tours, and their necessary and sufficient conditions. Then we will see Hamilton paths and Hamilton cycles. The third section is Dirac's theorem. It gives a sufficient condition to contain a Hamilton cycle. Let's start with this simple example. Drawing without lifting your pen. The question is, which of the 2 pictures below can be drawn in one go without lifting your pen from the paper? The answer is the first graph can be drawn in one go, but the second graph cannot. In the first picture, there are many ways to solve this problem. We can start from this vertex. Go up and down. Go back and turn right. Up, right, and down. Now it's done. If a vertex is neither a starting point nor an ending point, then each time passing through it, it corresponds to 2 edges. One comes in and one goes out. So the degree of each intermediate point should be even. If a vertex has odd degree, it should be either the starting point or the end point. But there are 4 vertices of degree 3. 1, 2, 3, 4 vertices of degree 3, which is a contradiction. What is an Eulerian trio? What is an Eulerian tour? Recall that a walk is a sequence of vertices V0, V1, V2 to Vk, and a sequence of edges Vi, Vi plus 1. This is an edge belonging to Eg. There is an edge between every 2 consecutive vertices. A path is a walk with no repeated vertices. Now we have the definition of a trio. A trio is a walk with no repeated edges. So we see that both paths and trios are walks. Moreover, if a walk has no repeated vertices, then it has no repeated edges. That is to say, a path must be a trio. If we describe it in the language of science, the set of paths is a subset of the set of trios. The set of trios is a subset of the set of walks. A path must be a trio. A trio must be a walk. An Eulerian trio in a multigraph G equals VE is a walk in G, passing through every edge exactly once. If this walk is closed, starts and ends at the same vertex, it is called an Eulerian tour. So in the example at the beginning of this lecture, to draw a graph in one go without lifting your pen is to find an Eulerian trio. Here is an example. In this graph, we can find many walks. For instance, a walk 1, 2, 3, 5, 2, 3, 4, 5, 6. In a walk, both vertices and edges can be repeated. A trio 1, 2, 5, 3, 4, 5, 6. In a trio, vertices can be repeated. Here 5 is repeated, but edges cannot be repeated. A path 1, 2, 5, 3, 4, 6. In a path, neither vertices nor edges can be repeated. This graph has no Eulerian trio and no Eulerian tour, which is a walk or a closed walk that visits every edge exactly once. We cannot find them. Now we turn to another example. In this example, we can find Eulerian trios or Eulerian tours. There are many trios. Here is one of them. C, A, B, D, C, B, which is an Eulerian trio because it covers every edge exactly once. In the graph below, we can find an Eulerian tour. A, E, C, A, B, C, F, E, D, A, which is also a special Eulerian trio. The starting point and the ending point are the same vertex. Remember that an Eulerian trio and an Eulerian tour should visit every edge exactly once. We look for some necessary and sufficient conditions of an Eulerian tour or an Eulerian trio. This problem began from 7 bridges of Königsberg. 7 bridges of Königsberg problem is actually the beginning of graph theory. This map is part of the city Königsberg, which is now called Kaliningrad. It's to the north of Poland. The problem was to devise a walk through the city that would cross each of those bridges once and only once. Euler proved that the problem has no solution. The difficulty he faced was the development of a suitable technique of analysis. This is the origin of graph theory. We can abstract the graph on the left into the graph on the right. Every vertex denotes a land, and every edge denotes a bridge. So the question is, does the graph have an Eulerian walk? Now we have the theorem on Eulerian tour. A connected multigraph has an Eulerian tour if and only if each vertex has even degree. That is, if and only if it's an even graph. In order to prove this theorem, we use the following lemma. This lemma says every maximal trio in an even graph is a closed trio. An even graph is a graph where all the vertices have even degree. We let T be a maximal trio. Now we need to prove that T is a closed trio. Suppose to the contrary that T is not closed. Then T has an odd number of edges incident to the final vertex V. Because each time we visit V, we pass through two edges incident with V, one coming in and one going out. But the last time we visit V, we only come into V and don't get out. So we pass through one edge at the last step. However, as V has even degree, there is an edge incident to V that is not in the trio T. This edge can be used to extend T to a longer trio, contradicting the maximality of T. Because T is a maximal trio, but now we have extended a longer trio. This shows that our assumption is false. A maximal trio in an even graph must be a closed trio. We use this lemma to prove the theorem. A connected multigraph has an Eulerian tour if and only if each vertex has even degree. The necessity is given first. Suppose G has an Eulerian tour C. Note that for an Eulerian tour, it starts and ends at the same vertex. If a vertex V was visited k times in the tour C, then each visit used two edges incident to V, one incoming edge and one outgoing edge. Thus, the degree of V dV equals 2k, which is even. This includes the starting vertex, because the first edge can be paired with the last edge at the first vertex. For the sufficiency, let G be a connected graph with even degrees. Here we see that an Eulerian tour is an even graph, but an even graph may not have an Eulerian tour. Only connected even graphs have an Eulerian tour. You cannot go along the edges from one connected component to another connected component. So the definitions of Eulerian tour and Eulerian trio are for connected graphs. Let T equals E1, E2 up to EL, where EI equals VI minus 1 VI. EI is an edge. Let T be a longest trio in G. Then by the last lemma, a maximal trio in an even graph is a closed trio. T is closed. That is to say, V0 equals VL. the starting point and the ending point are the same vertex. If T does not include all the edges of G, then since G is connected, there is an edge E outside of T such that E equals UVI for some vertex VI in T. We can always find an edge E outside of T. Because G is connected, so we can always find an edge E outside of T such that E has an end in T. Because T is a closed trio, T can be viewed as a trio starting at VI and ending at VI. But then we have another trio T prime from E to EI plus 1, EI plus 2, up to EL, and then to E1, E2, up to EI. This is a trio in G, which is longer than T, contradicting the fact that T is the longest trio in G. Thus, we conclude that T includes all the edges of T, and so it is an Eulerian tour. Now it's easy to determine whether a graph has an Eulerian tour or not. If it is a connected even graph, then it has an Eulerian tour. If it is not a connected even graph, then it has no Eulerian tour. An important corollary is a necessary and sufficient condition of an Eulerian trio. A connected multigraph G has an Eulerian trio if and only if it has either 0 or 2 vertices of odd degree. To prove the necessity, suppose T is an Eulerian trio from vertex U to vertex V. If U equals V, then T is an Eulerian tour, and so it follows from the theorem that all the vertices in G has even degree. If U is not equal to V, note that the multigraph G union E, where E equals UV, is a new edge. This new graph is an even graph. It has an Eulerian tour, namely T union E. It follows from the theorem that all the degrees in E union E are even. The graph G can be obtained from G union E by deleting the edge E. Thus, we conclude that in the original multigraph G, the vertices U, V are the only ones which have odd degree. So the proof has two cases. If U equals V, then it follows directly from the theorem. If U is not equal to V, then we can add an edge UV to the Eulerian trio. Then the Eulerian trio becomes an Eulerian tour. Now we prove the other direction of the corollary, the sufficiency. If G has no vertices with odd degree, then from the theorem it contains an Eulerian tour, which is also an Eulerian trio. Suppose now that G has two vertices UV of odd degree. Then we have a new graph G union E where E is a new edge with two endpoints U and V. The new graph G union E only has vertices of even degree, and so, by the last theorem, this new graph has an Eulerian tour C. Removing the edge E from C gives an Eulerian trio of G from U to V. We can see the trick here is, if the graph is not an even graph but almost an even graph, we can create a new even graph by adding edges. Here graphs in this page are not simple graphs, but multigraphs. We can also find Eulerian trio or Eulerian tour. In the first graph, there are exactly two vertices, B and C, with odd degrees. The degrees of A, D, E are even. Thus, it has an Eulerian trio. We can find an Eulerian trio B, A, D, C, D, E, B, C. In the second graph, the degree of every vertex is even, so it has an Eulerian tour. We can find an Eulerian tour C, D, C, B, A, D, E, B, C. Now we come to the second section, Hamilton paths and cycles. Eulerian trios and tours are considering visiting every edge exactly once, but Hamilton paths and cycles are considering visiting every vertex exactly once. A Hamilton path in a graph G is a path visiting every vertex of G exactly once. A Hamilton cycle in a graph G is a cycle visiting every vertex of G exactly once. A graph G is called Hamiltonian if it contains a Hamilton cycle. Hamilton cycles were introduced by Kirkman in 1985, but its name was after Sir William Hamilton, who produced a puzzle whose goal was to find a Hamilton cycle in a specific graph. Note that the year recorded in Sudakov's book is not true. The correct year should be in 1856. Then 1 year later, in 1857, the Icosian game was invented by William Hamilton. It's a game on the graph of dodecahedron in which one player specifies a 5-vertex path and the other must extend it to a Hamilton cycle. For instance, one player put 5 vertices here. 1, 2, 3, 4, 5. It's a path of length 4. Then the other player tries to extend it to a Hamilton cycle. This is a Hamilton cycle, a cycle that visits every vertex exactly once. This is a three-dimensional cube. The bold black edges form a Hamilton cycle. Now we seek some necessary conditions for Hamiltonicity. First, every Hamiltonian graph is two-connected, because deleting a vertex leaves a subgraph with a Hamilton path. The Hamilton graph still contains a Hamilton path after deleting a vertex. The next proposition is, if G is Hamiltonian, then for any set S, which is a subset of V, the graph G minus S has at most S connected components. This is to say, the number of vertices in S is greater than or equal to the number of components in G minus S. This proposition guarantees that G is two-connected because deleting one vertex leaves at most one component. After deleting any vertex, the graph is still connected. Let's see this graph below. S has 6 vertices. And G minus S has 4 components. 6 is greater than 4. Why does this happen? This is because the graph G is Hamiltonian. It has a Hamilton cycle, visits every vertex. For instance, we move along this cycle from a vertex of C1. When we move out of C1, we cannot jump to C2, C3, or C4 because they are components of G minus S. There is no edge with one end in C1, the other end in C2. When we move out of C1, the first vertex V1 must belong to S. And when we move out of C2, the first vertex V2 must belong to S. For the same reason, when we move out of C3, the first vertex V3 must belong to S. When we move out of C4, the first vertex V4 must belong to S. These 4 vertices, V1, V2, V3, V4, are different because every vertex is different with others on a cycle. So the number of vertices in S is greater than or equal to the number of components in G minus S. Note that we are comparing the number of vertices of S with the number of components, not the number of vertices in the components. Let's see the formal proof. The proposition is, if G is Hamiltonian, then for any set S, which is a subset of V, the graph G minus S has at most S connected components. Let C1, C2 up to Ck be the components of G minus S. Imagine that we are moving along a Hamilton cycle in some order, vertex by vertex. Let's say we are moving clockwise, starting from some vertex in C1. We must visit each component of G minus S at least once. When we leave Ci for the first time, let Vi be the subsequent vertex visited, which must be in S. each vi must be distinct because a cycle cannot intersect itself. Hence, S must have at least as many vertices as the number of connected components of G minus S. We can use the proposition to explain why this graph is not Hamiltonian. Because in this graph, there are two vertices. If we delete them, the graph is disconnected with three components. If this graph is Hamiltonian and we delete two vertices, from the proposition we see that the remaining graph will have at most two components. This is a contradiction. So this graph is not Hamiltonian. Here is another corollary for bipartite graphs. If a connected bipartite graph G equals VE with bipartition V equals A union B is Hamiltonian, then the size of A equals the size of B. Because a cycle in a bipartite graph visits the two partite sides alternately, one blue vertex, one red vertex, one blue, one red, one blue, one red. So there can be no such Hamilton cycle unless the partite sides have the same size. Below is a formal proof. By deleting the vertices in A from G, we get B isolated vertices, and so G minus A has B connected components. Thus, by the proposition, we conclude that the size of A is greater than or equal to the size of B. By symmetry, we can also show that the size of B is greater than or equal to the size of A. Thus, we conclude that A equals B. We need to say that the condition in the proposition is not sufficient to ensure that a graph is Hamiltonian. It's only a necessary condition. We can use the proposition to determine some graphs are not Hamiltonian, but we cannot use it to determine which graph is Hamiltonian. The graph G below satisfies the condition of the proposition, but it's not Hamiltonian. Indeed, one would need to include all the edges incident to the vertices V1, V2, and V3 in a Hamiltonian cycle of G. Because if there is a Hamilton cycle, it must contain V1, so it must contain the two edges incident to V1. For the same reason, the Hamilton cycle contains V2, so it contains the two edges incident to V2. Also, the two edges incident to V3. In this way, the vertex U in the middle would have degree at least 3 in that Hamilton cycle, which is impossible because in a cycle, every vertex has degree 2. So this graph is not Hamiltonian. Now we come to the last section, Dirac's theorem. This is a sufficient condition for Hamiltonicity. The theorem was given by Dirac in 1952. If G is a simple graph with n vertices, n is greater than or equal to 3, and if the minimum degree of g dot g is greater than or equal to n over 2, then G is Hamiltonian. This is to say, if every vertex is adjacent to at least half of the vertices, then G has a Hamilton cycle. The following graph is an example. There are 7 vertices, and this graph is a 4 regular graph. Every vertex has degree 4. From Dirac's theorem, we see that this graph is Hamiltonian. Actually, we can find such a Hamilton cycle. A, E, C, D, B, F, G, A. It's not easy to find such a Hamilton cycle, especially when the graph has many vertices. But from Dirac's theorem, it's easy to see that this graph is Hamiltonian. And here n over 2 is best possible. If this bound decreases a little, the conclusion is no longer true. Here we have 2 examples tells us that n over 2 is the best possible minimum degree bound. The first example is the graph consisting of 2 cliques. One clique is of order the biggest number less than or equal to a half of n plus 1. The other clique has order which is the smallest number greater than or equal to a half of n plus 1. And here n over 2 is best possible. If this bound decreases a little, the conclusion is no longer true. Here we have 2 examples tell us that n over 2 is best possible minimum degree bound. The first example is the graph consisting of 2 cliques. One clique with order floor of n plus 1 over 2, and the other clique with order cell of n plus 1 over 2. Here, floor of n plus 1 over 2 denotes the maximum integer less than or equal to n plus 1 over 2. And the cell of n plus 1 over 2 denotes the minimum integer greater than or equal to n plus 1 over 2. These 2 cliques share a vertex, share exactly one vertex. This graph can be drawn as below. So we can calculate its minimum degree, which is the floor of n minus 1 over 2. But it is not Hamiltonian. It is even not too connected, because we can find that there is a cut vertex in this graph. The second example is a complete bipartite graph. If n is odd, then the complete bipartite graph with one part n minus 1 over 2 vertices and the other part n plus 1 over 2 vertices has minimum degree n minus 1 over 2, but is not Hamiltonian, because we have known that a connected bipartite graph is Hamiltonian, then the two parts must be of the same size. From these two examples, we see that the minimum degree bound n/2 is best possible. How to prove this theorem? First, we need to know that the simple graph G has at least 3 vertices, because if G has exactly 2 vertices, it is not Hamiltonian, but it satisfies the condition. The minimum degree of K2 is a half of the order. To prove such a graph must be Hamiltonian, we suppose to the contrary that there is a non-Hamiltonian graph satisfying the hypothesis. Then there exists a maximal non-Hamiltonian graph. A maximal non-Hamiltonian graph. What is a maximal non-Hamiltonian graph? It is obtained from a non-Hamiltonian graph by adding edges. If there is an edge, after adding it to the graph, it is still non-Hamiltonian, then we add it to the graph. If there is another edge, after adding it to the graph, it is still non-Hamiltonian, then we add it to the graph. Go on with this procedure until no edge can be added. That is to say, if you add any one more edge to the graph, it becomes Hamiltonian. So we keep adding edges until it is a maximal non-Hamiltonian graph. Then we stop. Because if you add any edge to this maximal non-Hamiltonian graph, it will become a Hamiltonian graph. Now the maximal graph has minimum degree at least n/2. By maximal, we mean that for every pair UV of non-adjacent vertices of G, the graph obtained from G by adding the edge E equals UV is Hamiltonian. If G is a complete graph, then of course G is Hamiltonian. If G is not complete, we choose two non-adjacent vertices U and V. Because G is maximal non-Hamiltonian, if we add a new edge between U and V, then G union the edge UV contains a Hamilton cycle. That means G contains a Hamilton path from U to V. Every vertex of G is on this Hamilton path. You see, the maximality of G implies that G has a Hamilton path, say from U equals V1 to V equals Vn. Because every Hamilton cycle in G union E must contain the new edge E. How to get a Hamilton cycle in G? We use most of this path V1, V2 up to Vn with a small switch to obtain the Hamilton cycle. If some neighbor of U immediately follows a neighbor of V on the path, like in this graph, U is adjacent to Vi and V is adjacent to Vi minus 1. In this way, we can find a Hamilton cycle. The cycle is U Vi plus 1 to Vn minus 1 V Vi minus 1 Vi minus 2 to V2 to V1, which is U. So this is a Hamilton cycle. Our proof is done. The next question is how to find two such edges. Because the minimum degree of G is n over 2, and this is a Hamilton path, we see that U has many neighbors on the path, and V has many neighbors on the path. So we can find a neighbor of U immediately follows a neighbor of V. The formal proof is, to prove that such a cycle exists, we define two sites, S and T. S is the site of all I, such that U and Vi plus 1 is an edge in G, and T is a site of all I, such that V and Vi is an edge in the graph G. If S and T contains a common number I, that means a neighbor of U is the successor of a neighbor of I. Then we can find a Hamilton cycle. So we need only to prove that S intersection T has at least one element. Summing the size of this size yields S union T plus S intersection T equals S plus T. This is a simple result in set theory. S equals du and T equals dv. S plus T equals du plus dv is greater than or equal to n. Because V and Vn are the same vertex, neither S nor T contains the index n. This implies that S union T is less than n, and hence S intersection T is greater than or equal to 1, as required. So we can find a Hamilton cycle in a maximal non-Hamilton graph. What? A Hamilton cycle in a non-Hamilton graph, which is a contradiction. This implies that our assumption is false. There is no non-Hamilton graph satisfying the hypothesis. Every graph with the Dirac condition is Hamiltonian. Now the proof is done. 8 years later, Orr observed that this argument uses only that du plus dv greater than or equal to n. Here, du plus dv is greater than or equal to n. The proof did not use du greater than or equal to n over 2 and dv greater than or equal to n over 2, but du plus dv greater than or equal to n. Therefore, we can weaken the requirement of minimum degree n over 2 to require only that du plus dv greater than or equal to n whenever u is not adjacent to v. So from the proof we see that we can weaken the requirement of minimum degree n over 2 to require only that du plus dv greater than or equal to n whenever u is not adjacent to v. This is Orr's theorem. If G is a simple graph with n greater than or equal to 3 vertices, such that for every pair of non-adjacent vertices uv of G, we have du plus dv greater than or equal to n, then G is Hamiltonian. We see that this is a weaker condition comparing with Dirac's condition. From du greater than or equal to n over 2 and dv greater than or equal to n over 2, we have du plus dv greater than or equal to n, but the reverse is not true. Here is a graph with 7 vertices and minimum degree 3. Minimum degree 3. It does not meet the condition of Dirac's theorem. Dirac's theorem asks the degree of every vertex should be at least a half of n. 3 is not greater than or equal to a half of 7. But it meets the condition of Orr's theorem. For every pair of non-adjacent vertices uv of G, we have du plus dv greater than or equal to n. So it contains a Hamilton cycle. Thanks for watching this video. See you next time.